This is video 6 of Unit 12. In this video we will talk about heating curve calculations. Now if you remember from a previous video, the heating curve looks like this. And what we have is we have two places that are flat. This is melting, and the other flat place is boiling or vaporization. And they're flat because the temperature stays constant when you boil or melt. The other three are heating of the solid, heating of the liquid, and heating of the gas. What we'll do now is we'll apply calculations to each portion here, and we'll give you two types of equations, one that talks about the flat portions, the other one that talks about the curved, or not curved, but the diagonal portions. So before we can dive in, we have to define a few terms. The first term is molar heat of vaporization. This is the amount of energy needed to vaporize 1 mole of a liquid. Now, every substance has a different heat of vaporization. Every substance has to have a different amount of heat put in to boil it. So what we're talking about here is we're talking about the boiling portion right here. Water, for example, takes a certain amount of heat to boil. Something else, say for example iron, takes a different amount of heat to boil. And this is all related to the strength of the forces, you can say, between the molecules, the intermolecular forces. Then a similar concept is molar heat of fusion. This is the same idea but applied to melting. If you want to melt 1 mole of a solid. And so this would actually talk about the first flat line, how much heat it takes. Again, water takes a different amount of heat to melt than any other substance, and this is logical. The units, by the way, are kilojoules per mole. This is why it's called the molar heat, and kilojoules is a unit of energy. We've seen this before. Energy is actually derived in joules, usually, one of the units. Now, a similar concept is specific heat capacity. This is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. So this is when you're not boiling or melting. This is in the middle, you could say, or not in the middle, but in the diagonal portions of the heating curve, these portions right here. And so different substances take in heat differently. For example, if you take a look at water, water's heat capacity is 4.179, whereas iron's heat capacity is 0.450. And so iron only takes this much heat to heat up by 1 degree Celsius, but water takes much more heat to heat up by 1 degree Celsius, actually almost 10 times as much. And actually, the more dense the metal, for example, gold is very dense, the lower its heat capacity, because a very dense metal has a very high conductivity of heat. Heat conductivity is the idea. This column does the same thing except for joules for 100 grams, if you have 100 grams of a substance, but you can see a similar picture. Different substances take different amounts of heat just to heat up. This, by the way, is why water is used to power to cool and warm up human beings, because water has an unusually high heat capacity, very unusual for water. And this is also why whenever you're swimming, the water, once it's warmed up, it's very comfortable to swim in, because at nighttime the heat doesn't leave. You can actually come back the next day, or you can even swim at night if you'd like, and water can take in heat very well. So water takes in heat very well and then holds it. It has a very high heat capacity. That's what we mean by heat capacity. So here's an overview of water, because we will be using water in general. Here is the specific heat of ice. This is how much heat is needed to warm up ice. Here's the molar heat of fusion of ice. Here's how much heat it needs to melt ice. Specific heat of water. Here's how much heat is needed to warm up water. How much heat is needed to boil water or vaporize water. And again, how much heat is needed to then warm up steam. These are the 1, 2, 3, 4, 5 portions of the heating curve of water. And we will actually do some calculations with this. So if you take a look then, you've got the heating curve with the different 5 portions. There are 2 equations we will apply. The first equation will deal with the 1, 2, 3 diagonal portions. And you'll notice the equation says heat equals specific heat times mass times change in temperature. Sometimes this is called C, the specific heat, M for mass, and then delta T for temperature. And very often you'll see it designated this way. And sometimes it's called the MCAT equation, MCAT, because what they do is they put mass first and then easy to remember. There are three portions to this equation because it refers to the three diagonal portions of the heating curve, which makes sense. The other equation says heat equals moles times heat of vaporization. Now this one refers to the two flat portions, and it does not have a third component. It only has two parts, so you can say it has moles times heat of vaporization. So heat, usually vaporization. It can also be fusion, depending if you're melting, if you're here, or if you're boiling, if you're here. And the way to remember it is there are two flat portions. Those two belong to the equation that has two portions to it. And the reason it only has two portions is because you don't increase the temperature as you're boiling or as you're melting a substance. Okay, so let's go ahead and apply these two equations to a few problems. Okay, the first problem is how much heat is needed to boil 3.4 moles of water. Now the first thing to do in a problem like this is figure out which portion of the heating curve we are talking about. Because we're boiling, we're actually talking about this portion right here of the heating curve. Now the heat of vaporization is given to us here. So we will apply the second equation, the one that has two parts, because we're referring to a flat line, that there are only two flat lines. So you'll use the equation that says heat equals moles times heat of vaporization. In this case, we're vaporizing, so it's going to be heat of vaporization. All right, so we have moles as 3.4. Easy enough. Heat of vaporization is given to us as 40.79. And I'll put in the units as kilojoules per mole. And if you do this calculation, go ahead and do this in your calculator, 3.4 times 40.79, you come out with 138.686. We want to use significant figures, so we have only two. Let's get it up to 140. And in this case, the units will be kilojoules. This is the unit for heat, 140 kilojoules, because the moles cancel out. So it takes 140 kilojoules if you want to boil 3.4 moles of water. Now the water is already at the boiling point. All we're doing is we're boiling it. And this is how we do it. We first find the equation that applies to it and then plug the numbers in. So not too bad. Let's go ahead and try the second problem. The second problem says how much heat is needed to raise the temperature of 15 grams of water from 15 degrees to 45 degrees Celsius. If you take a look at the heating curve, it has 5 parts. What are we asking here? We're asking to heat water. Now, heating water is this portion right here of the heating curve. So we'll use the equation that has 3 parts because there are 3 diagonal portions. So we will use the equation that says heat is equal to specific heat times mass times the change in temperature. The specific heat of water is given to us as 4.18 joules per gram degree Celsius. That's what goes in here. So 4.18 joules per gram degree Celsius. The mass is given to us as 15 grams. And the change in temperature, now the change in temperature, you have to subtract the two numbers. In fact, the change in temperature, delta T, is defined in detail as the temperature of the final minus the temperature of the initial. So if you do 45 minus 15, that's how you get 30, exactly right. And so 30 degrees Celsius. And if you want, we can say we got this by doing 45 minus 15. What you'll see is that grams cancel out, degrees Celsius cancel out. We're going to be left with joules for our answer. So go ahead and calculate this out, multiply this through. You get yourself 4.18 times 15 times 30. And you get yourself 1,881. Now again, we have 2 significant figures, so let's just do 1,900. Again, the units are going to be joules. So if you want to heat up 15 grams of water by 30 degrees Celsius, it'll take 1,900 joules. Now in the previous example, we actually had kilojoules for our answer. In this, we have joules. We can convert this from joules to kilojoules actually by dividing by 1,000. And we could get ourselves 1.9 kilojoules. That's also a good answer. You have to realize that whenever you're using the diagonal portion, you're going to be ending with joules. Whenever you're using the flat portion, you'll be ending with kilojoules. This is because it takes quite a bit more heat to boil or to melt than it does just to warm up. Because when you're boiling and when you're melting, you're actually separating the bonds. When you're heating it up, you're really not separating the bonds of the molecules. It takes a lot of energy to break bonds, and that's the idea. So go ahead and try a few examples of your own. Try this example, and we will talk in class. So this concludes for us Lesson 6 of Unit 12.